Finally, we want to complete this topic of different curvilinear coordinates with the notion of how we take the derivative in this new coordinate system. Right, so that is an important aspect. So before that, we introduce the differential operators such as gradient, divergence, and curl or rotor in the our regular coordinate system, our Descartes coordinate system. So now in the curvilinear coordinates, you can recall that for some differential equations, for example, when you were in the geometries like considering a tube, for example, and so you have seen there are additional and strange terms and multiplicators that come in as a factor 1 over r, etc. of radius. And the reason for that is that when we take the derivative of differential operators in curvilinear coordinates, we actually through the derivation we do see additional terms coming up. Now, so let's start again. So here is our defined contravariant basis. That's how we just defined it in the previous lecture. And so now we are going to write our definition for gradient, divergence, and other operators. And now we're going to convert it towards something that will have these components, because we want to write them in the in the new coordinate system. Now let's start from the gradient, and this was our definition for the gradient. So okay, so we take some quantities here. So for the just for this example, for the sake of this discussion, so it will be a vector that we take a gradient, and we already know that the result will be a second order tensor. We take it, and so we take it with respect to the position vector x, and so which is written in this way, right? So we have the components of x, and we have the basis vector e in our Cartesian coordinate system. All right, so now what we're going to do, we want to so this is our original definition of the Cartesian coordinate system. Now we want to transform it into the curvilinear coordinate system. So to do that, so we first do our regular chain rule in the differentiation. So we use that, so we can write that we can take the derivative of a with the components of alpha, and I remind that alpha r, so we have so these alpha represent the components of our new coordinate system. So that's for cylindrical coordinate there was an angle phi, there was a radius, and there was a height z, right? And so we can we're using now the chain rule, and we write this dA dx expanded as dA d alpha dxi, and this is again can be moved here because this is a scalar, and basically the tensor product only applies to what is bold, to dA and e here. Now with that we also can look into what is the on the right hand side here, on the very right part, and you can notice that this is nothing but our definition of the contravariant or dual basis vector as j in this notation, because we have j here. All right, so we can now substitute it with sj, and so finally our result will be nothing but this. So this part is preserved, and so instead of the part that we multiply with tensor product from the right, will be nothing but sj. So now you can compare to the original definition of gradient in our Cartesian coordinate system, and you see that the structure actually didn't change. So we still take so that's this is our basis vector, this is our contravariant basis vector and its component that we take the derivative of a with respect to alpha. And again, a can be written in different coordinate system, can be written in Cartesian, or it can be written in curvilinear coordinate system, so depending on what is more convenient for us. And so if we write it in the curvilinear of, say, for example, cylindrical coordinate system, so then we take the derivative of that, will be more convenient taking derivative with respect to alpha, which alpha will stand for radius, for angle phi, and for height z in this case. So now let's go next. Let's look into the into the operation of curl or rotor, so which is essentially reminiscent of a vector product with certain differential operator, and so our definition here again for that was this. So we take the derivative with respect to the components of that vector, and that there is a vector product here. And so then we can again use the chain rule, basically exactly the same way how we did here. So we can just rewrite it. Yes, we can write d alpha dx d alpha, so same the chain rule. So basically expanding it here, and the part d alpha dx could be written anywhere on the left or the right, because it's scalar. It doesn't matter where we put it. And again, the vector product applies for these for these here that were in bold. So these basically vectors here, e and a. So they are multiplied by vector product, and this is just a scalar multiplicator. Of course, the order of indexes is important, but they are not. This is not affected by the vector product here. So this is applied on e and a. And so we could write on the explicitly here. So this part is equal to this multiplied by that. So because we again use the chain rule, differential rule, and and now again we notice once again that this is nothing but Sj, our contravariant basis vector or dual basis vector. And so we can just substitute that in here, and you will see that the structure again didn't change. It works exactly the same way as it worked for us for the Cartesian coordinate system. So this is our basis vector. Here we also have our basis vector, and we multiply the actual vector that we take the derivative of with respect to the coordinates that we have chosen to work with, and exactly the same here. So in this case it's simple, our Cartesian coordinate systems that we typically work with, and in this case it will be a new coordinate system. Again, it can be cylindrical one or spherical coordinate system that we would prefer to work with. Now finally let's go to higher order. So let's take a second order derivative, derivative of a second order tensor, and especially we'll take a divergence, which is very important operator, which is very important for us. Actually, the one that appears a lot in the equations that we are solving in the continuum mechanics, the divergence of a second order tensor, again typically stressed. All right, so and the definition again is this. So we take the derivative with respect to the position vector x, so these are components, and again the multiplication here between second order tensor and the vector ei, there is a, so we mean that there is a dot product, so the result of that multiplication will be a first order tensor or vector. And so when we multiply tensor with a vector, so the tensor acts on the vector, produces a new vector. So that is what we discussed about tensors. And now, so in similar manner again, as we already have done it previously for gradient, so we can use the chain rule here, and just write, so d when we take we differentiate something with respect to x, we can actually write it as a differentiation with respect to something else, in this case alpha, and then that alpha we need to differentiate with respect to x, so that's still the same result here. And once again, here we very quickly again notice that this is nothing but our dual basis vector or contravariant basis vector as J. So we can replace it, and you already should not be surprised that at the end we get exactly the same structure as we had here. So this is our basis vector, and here is our derivative of that second order tensor with respect to the components. And again, so just for sake of the example, let's say it was cylindrical coordinate system. So alpha j would stand for radius, angle, phi, and the height z. All right. So now let's see what else we need. We need to have here. How can we actually specify it for a cylindrical coordinate system, for example? Okay, let's look at the gradient as an example in cylindrical coordinate system. Now, so we derived that the gradient in a curvilinear coordinate system can be written in a general way like this, right? So we didn't specify alpha just yet, but now since we're working in the cylindrical coordinate system, so then our alpha, they had the meaning again. So this radius r, or phi, angle, or the height z that we mentioned. And of course there's 1, 2, 3 here, superscripts. They are not powers, but the indication of the indexes. Sometimes people use the parentheses here in the superscript to kind of avoid the notion of using of the notation, to avoid confusion with actual power when we take so in this case it's of course indexes. Alright, so now we can write more specifically what the gradient of a vector will be. So of course the first is the derivative with respect to radius and with respect to the angle and phi, and then the last one is with respect to z. And so and this our contravariant basis vectors as r, as phi, and as z were given like this. So right, so we actually defined and derived them, and so there was one more comment with that. Remember that we actually wanted, so you can see even from here that some of them are not unit vectors. So for example, as r and as z are unit vectors, but as phi is not a unit vector, actually depends, and the length of that basis vector depends on r. And for us, it's not really very convenient to have them not unit vectors. Also, it's possible to work with that, but it's more of a common approach to use unit vectors in the definition. And for that, if you remember, we introduced the normalized, so-called normalized basis vectors, when we just calculated the length of these basis vectors and divided them by this number, by their length. And so in that way we obtained the unit vectors, basis vectors that also unit vectors, right? And you can see by the structure, so basically the only one that was affected is this g phi, right, because it has a factor of r here. And so that's and now you have so we normalize it by the length r. Now, if we want to write now this equation for gradient for gradient of a vector in a cylindrical coordinate system in terms of the unit basis vectors rather than the basis vectors as, so then we need to take into account this factor of normalization here, right? So, for example, SR is exactly the same as GR, so we don't need to do anything. We can just substitute here GR, so it will be the same thing. The same with SZ, because it's trivial, so it was E3 and here it's E3, so they're the same. So I can just easily write SZ, or I can say GZ. But now with SF or Sphi, the one that corresponds to the angle, the basis vector, actually if I have here, so we need to multiply that with 1 over r, and then we can write GF, right? So this is because the factor with them is 1 over r. So we basically multiply gf with r, sf with r, and we obtain gf. So to make it right, so if we here to make add the factor 1 over r, and as we go from this expression to this expression. And so now you have this is the expression that we can use a gradient of a vector in cylindrical coordinate system, written in terms of the of the unit basis vectors, will be written like that. And here is the factor of 1 over r, that the basically manifestation of the our transformation of differential operators into the cylindrical system, and that's what a similar manner things will start like this. The factors, multiplicators will appear in your differential equation. Again, if we consider a tube and you write all the equations for that, these factors as 1 over r start to pop up there, and if you don't know how we arrive to that, maybe a little bit surprising. But now you can use it with the comfort of knowing what is the reason and why they appeared here. One more thing is that if we look at 177, we can notice that basically the basis vectors, also they're still unit vectors, they are not independent of the coordinates, all right? So they depend on phi. So and that wasn't for us the case for us in the Cartesian coordinate system when we took the derivative, for example, with x1 or x2. So the basis vectors, of course, didn't depend on these components x1 and x2. In this case, as you can see, gr and g phi actually explicitly depend on the angle phi. And so if we encounter a situation when we need to take the derivative of some quantity, of some tensor that has this, we will need to take into account this dependence. So we cannot just assume that they are not dependent. They are actually explicitly dependent on the coordinate. And for example, if we need to differentiate further this with respect to some coordinates, so we'll need to keep in mind that gr and g phi are not independent. Actually, going to write that explicitly, what components are not independent. And again, so as you can see, gr and g phi are dependent on phi. So then we can just go ahead and summarize all of this and write, okay, so it's obvious for us that all the possible derivative with respect to r of all these basis vectors in cylindrical coordinate system will be zero vectors, right? Because they never depend on r. However, once we encounter dependence on phi, need to take the partial derivative with respect to phi, then so the result will be this. So, for example, let's take the derivative of gr with respect to phi. So, and okay, so the result will be this. So we'll take instead of cosine phi and sine phi, we'll have again cosine phi, and here we'll minus sine phi, and as a result, so the derivative of gr with respect to phi will be exactly the same as g phi, right? So that's exactly what we have here. Now, if we are going to take the derivative of g phi with respect to phi, so instead of sines here, we'll have, so minus will preserve, so we'll have minus cosine phi, and then take the derivative of cosine phi, so we'll get minus sine phi. So basically we have exactly the same as gr here, but with minus here, because there are minus here, and there are one minus will appear here when we take the derivative. And so we can say that so basically the derivative of g phi with respect to phi will be nothing but minus gr. So that, and I indicate here in the blue these that are not zero. But other than that, of course, obviously z doesn't depend on phi, and so only two components of such a derivative that were not zero. Now let us briefly look into another curvilinear coordinate system that is quite important and very useful. So we're going to look into the spherical coordinate system. Now, in this case, again, so the motivation can be different, and it's basically a setting of the boundary conditions and things that you're going to solve. But a few examples would be, for example, pressure vessels that would be very convenient to treat and solve the equation, predict stresses as a result of the inner pressure in the pressure vessels. It can be a problem for a spherical balloon, that again you have an inner pressure and you still have the spherical symmetry of the balloon, and that will extend as you increase the pressure. And some adaptation of that, so you can think about, for example, cells that probably will never adopt exactly the spherical shape, but still can be approximated to that. And some quite many situations when you can use the spherical symmetry to simplify your problem, so you don't need to solve it. And it appears that actually, of course, in such situations, again, as we go back to cylindrical coordinate system for tubes, it's much more convenient and effective to write all the equations in the curvilinear coordinate system rather than trying to still work in the Cartesian coordinate system, especially when you think about applying the boundary conditions. That's where it comes into play. Now, all right. So in this situation, we have this obviously will be somewhat more complicated because, well, in cylindrical coordinate system, for example, the coordinate z just coincide with our coordinate e3, and so we basically had only one angle and radius in plane. Now, of course, we only have one radius here too, but now we have two angles that define the position, right? So we have angle phi as we had before, right? So that's in plane, let's call it in plane angle, and we have out of plane angle theta as well here, as opposite to the previous case of cylindrical coordinate system. And so once we say what is our phi is, then in radius we can identify the position or projection of that on the plane x1, x2. But then if we really want to know what is the coordinate of that actual point, we also need to say what is the angle to actually find what is the actual position of that point here in the space. So we have again we still have these three alphas, right? So that is, in our case, we have alpha that is so the radius indeed, and so we have also the out of plane, let's call it the angle theta, again just another angle, so defined as the angle between e3 and the position vector r, and so we have our in plane alpha phi. And now you can see that basically again so the coordinates x so once this vector is given, that so it's expressed in terms of the position in plane. So you can see that there is a part of r cosine phi, right? So and r sine phi. So these things we had also in the cylindrical coordinate system, and then we project them further up. So basically this vector is projected here, right? So and that is done by this addition of sinus theta. So you can if you have time, and it's a good exercise to actually see how these components come to this expression from simple geometrical consideration of the angles. Again, similar to what we already considered for the cylindrical coordinate system. The only thing is that after you calculate the in-plane position here, so there is also the geometrical angle theta that also defines where exactly will be here and also the x3 here, right? So that's so, and in that sense, it's somewhat a little more complicated that we obtain here. Complicated, not extremely complicated, but a little bit more involving that in the cylindrical coordinate system. So now, so we would like maybe to have the inverse relationship if we want to calculate dependence of r and phi and theta with respect to our Cartesian components x1, x2, x3. So we can write that again partially on describing the our on geometrical basis. Obviously, that, for example, the radius you can calculate based on the coordinates as just root square of the square sum of the components. So this is also the obvious one. And so for the angle theta, yeah, so there is a component x3 here, right? The projection here, and now you just divide it by the length of that vector, right? And so then you obtain the cosine theta, and then you can calculate theta by taking the arc cosines of that number, again projection x3 divided by the length of r, which is here. Now phi is something that we already looked into before. So in plane consideration for cylindrical coordinate system. Now what is important to us to actually to come and say what are these g, r, g, phi, and g theta, how they are expressed. And so the definition for them is still the same. Is just now we need to use the relationship between the Cartesian coordinates components in Cartesian coordinates and in the spherical coordinates to define them. But the relation, the covariant basis or contravariant basis, are the same. So the only one more step that we need to do is similar to what also was done for the previous case of cylindrical coordinate system. We want to write it as a normalized unit vector. So then we calculate the length of those and divide this contravariant or covariant basis by their lengths, and so then we obtain the same result of our new basis vectors in spherical coordinate system that we denote also g theta, phi, and g r. And they also orthogonal, so that's important for us. So they are similar to the previous case. Okay, and so they can be written in the following way. So again, can be on basically following exactly the same procedure as before by using the expressions that we just derived, that we had here, and define the relationship between x components x1, x2, and 3, and r, and phi, and theta. So then we can take all the derivatives and with some manipulation can derive how they look like in the for spherical coordinates in terms of 1 and 2. Now, and as you can see again, and we will look into that just very soon, is that now the dependence of these basis vectors in spherical coordinate system obviously depend on the components of the coordinates, right? So if we take derivative with phi, with respect to phi, we will have dependencies of, in all the components. Or if we take the derivative with respect to theta, then you will get the gr, for example, is still has a dependence on theta, and g theta also depends on theta, but g phi doesn't. So we'll look into that, what how the what are non-zero and what are zero, and but obviously there is no dependence on r, and that is the direct result of our normalization, right? So we eliminated that when we made it the unit vector. All right, so with that, so we can also write how the gradient will look like. Again, so basically what the way, you will follow exactly the same ways as we did for cylindrical coordinate system, and just for sake of time, we'll not do it here, just to give the result in that. And as similar to to the previous case, you start seeing that okay, so in a similar ways with the gradient in the Cartesian coordinate system, you take the derivative with respect to your components r, theta, and phi, and multiply it with the basis vectors that tensor product with these basis vectors that correspond to that one that took the derivative with, right? So in Cartesian coordinate system that would be x1, and here x1 that will be e1, here it will be okay x2 and e2 and x3 and e3. And we still differentiate the same vector a here, right? Now you notice that similar to what we had in cylindrical coordinate system, we have factor 1 over r here, and moreover we also here when we take the derivative with respect to phi, we also have additional factor here 1 over r, the same factor here, but also sinus theta. And so this is an important addition here, so it cannot be important to keep it with us, otherwise we'll be not doing this in a proper way. And so once again we'll finally look into how the if we take the derivative of the basis vectors in spherical coordinate system, so they will not necessarily be zero. That's again a difference with the Cartesian coordinate system, but also there is a difference with the cylindrical coordinate system. And here you can see that we have so more terms that are non-zero, right? So again, all the dependencies with respect to r are zero. So, but we already mentioned there is no dependence on the position on the radius. So all of them are zero. But then when it takes the derivative with respect to theta, and there will be similar procedures that you obtain here because of the similarity of gr and g theta. And when we take the derivative with respect to theta, the cosine theta will produce your sine with the change of the sine become negative, or change your sign, and then so that will happen here too, and then you will have lines cosine theta here, and you will see that basically that will look exactly like gr. It's the only one that you will lack here, that minus sign here, and so you can so that's why you have the minus gr. And that's similar what we had also with the cylindrical coordinate system. So and then you can also go on and can take the derivative of g phi with respect to phi, and see how what will be the result here. And and so I can, yeah, so if you have time, that's a good exercise to go over this and derive this derivative. So if you wonder if there anything that is not clear here. All right, so but bottom line here is that obviously so there are things in between when we go from the Cartesian coordinate system to curvilinear coordinate system. The way how we take the derivative is very similar, but we need to follow all the steps so we don't lose the terms. And another important point to remember that is not actually obvious until you start thinking about it, that the base vectors that define the position of the quantity in our new coordinate system, either cylindrical, spherical, curvilinear one, actually do depend on the coordinate, on the position. And so this is important to take into account, especially when you start taking derivatives, because then there will be some things that are not zero. Well, and this is at first may not be as intuitively clear because we are so used to work in the Cartesian coordinate system and use the curvilinear coordinate system less frequently. Also, again, in many cases, actually the coordinate systems that you want to use, and that's more effective, and basically I would say would be the only effective way to solve a certain problem, depending on the geometry and hence the boundary condition, etc. All right, so with that we finish our introduction to tensors. So the first module is finished, and we will go on to the second module of our course. We'll talk about kinematics and how deformation happens. See you soon.